Joining today's session. My name is Irina, and I'm the event planner for the Redmond Reactor space. Before we get started, I have a few things to go over. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience as well as our presenter. We encourage engagement in the chat, but please be mindful of your commentary, remain professional and on topic. Useful links will also be shared in the chat. This session is recorded and will be available on demand in 24 to 48 hours on the Microsoft Reactor YouTube channel. Which brings us to today's session. The session will run approximately 1 hour with questions throughout, and I'll now turn it over to our speaker for introductions.
Awesome. Thank you very much. Good morning, good afternoon, good evening. Hello, wherever you are in the world, and welcome to lesson 2 of IoT for beginners. So thank you for everyone who joined. If you joined us last week, we went through just a very basic introduction to the Internet of Things and what it was all about. Today, we're doing a bit more of a deeper dive into the things, a deeper dive into kind of the hardware components of an IoT solution. So welcome. I know there's a few of you who have been very keen. Chandra, welcome. I saw you say hello on the chat about 40 minutes before the stream started. So welcome. And Kamal, welcome. I remember you from last week, so thank you very much. Now, this is a session all about a deeper dive into IoT, but this can be very much a question and answer type session if you want. So please engage in the chat. Let me know what IoT things you're working on, ask questions, and let's kind of just have a bit of fun learning about the Internet of Things together. So if you're new to any of these shows, I'm Jim Bennett. I'm a regional crowd advocate at Microsoft and an absolute IoT nut. I have literally behind me is more IoT devices than I can imagine. I've got like 5 on my desk as it is, and I love IoT gadgets and gizmos. So if you want to follow me for IoT content, I'm all over the internet at Jim Bob Bennett, Twitter, GitHub, Instagram, LinkedIn. Please connect. If you want to chat IoT, feel free to reach out. I'm a friendly chap, always happy to talk IoT with folks. And Babak says, hello, everyone. Hey, Babak, welcome. Glad to have you here with us. Now, this month, July, is a very special month for IoT because this month is July-OT. Yes, we have a whole month all about IoT based on the beautiful pun that is July-OT. So all throughout July, we celebrate the Internet of Things with a whole lot of great content to help you learn, grow, build up your IoT skills. And everything you need to join in July-OT is at julyot.dev. This is our home for July-OT. So if you head to julyot.dev, you land here, and we've got a load of great stuff on here to help you. We've got things like a cloud skills challenge. So if you want to learn about the cloud skills for IoT, you can join this challenge and work through a whole of curated learning content. We have digital swag. So if you want animations for social media, you want to print yourself some stickers, you want desktop backgrounds or via video chat backgrounds, we have got all the stuff on there to do that. We've got a load of live streams coming up. This is one series. We've got a whole load more throughout July. And if there's any meetups happening, we had them here. Only had one so far. There's going to be more coming. A load of IoT resources to get going. And then every day we publish one or more pieces of great content around IoT. So today was IoT for Beginners Lesson 2, where you are now. That's one of the things. And some content around the .NET Nano Framework. Kind of every day we've got something where we've got covering like Nano Framework, we've got build a classic Altair using an IoT device, plug and play develop the PnP flow, a load of stuff and more stuff coming all throughout the month of July. So keep checking out julyot.dev, head there every day to get more great Internet of Things content every day throughout July. Carol says, Le vendredi, c'est long. In French. Oh, my French is terrible. The Friday is, I don't know what lot means. This Friday is, the Friday is IoT. Yes, this Friday is IoT. Oui, c'est très bon. Yeah, great to have some French. I did a little bit of French at school, and I'm terrible at it. So yes, le vendredi c'est très bon pour, I don't know how you say IoT in French. IoT? I don't know. That's cool. Gert says, hi all. Hey, Gert. How you doing? Ethiana says, what are we talking about? We're talking about the Internet of Things. RCL044 also asks, always about the Internet of Things. Yes, we are talking about the Internet of Things today. This is the second in our series of IoT lessons. We did one last week, one today, and we've got one next week and one the week after. So we kind of worked through the first 4 lessons of IoT for beginners. So everything I'm doing today, everything I did last week, and everything I'm doing the next 2 days is based around IoT for Beginners, our free 24-lesson IoT curriculum. It's aka.ms/IoT-beginners. We'll get this link, angelit.dev. In fact, let me just drop these links in the chat for everyone. /IoT.dev. This is where you want to go for great IoT stuff. And then you want to do IT for Beginners, aka.ms/IoT-beginners. I can type. Yes, I can type. So IT for Beginners is our free 24-lesson IoT curriculum, and that's what we're basing these lessons on. It's on GitHub. It's completely open source, MIT licensed, so you can do what you like with it. So if you want to just learn from it, cool. You want to take what's there and teach it in the classroom, cool. You want to take what's there, rip out little bits and pieces and rebuild your own learning content, cool. It's here, it's free, it's for you to learn about the Internet of Things. It's 24 lessons. We've got 4 lessons that we're working through at the moment, which is our kind of introduction to IoT. And then it goes from a journey from farm to table. So we start with digital agriculture, with automated watering systems. We look at logistics to get your food to processing plants or factories, where we look at GPS data and geofences. We use AI on the edge to do fruit quality monitoring. We do more AI on the edge to do stock monitoring in retail to make sure there's food in the shelves. And then some more AI, because AI and IoT go together so well, to actually build your own smart timer. So if you've ever done, Alexa set a 5-minute timer, we teach you how to build that. So 24 lessons, all the content is there, all the code is there. We've got video content, written content, quizzes all the way through. It's all hands-on. So we don't just explain how to build a vehicle tracking system. You actually build it with real hardware. So it's proper hands-on projects all the way through. And what's cool with the hardware is, where's the really cool link? So what's cool with the hardware? If you want to actually use hardware with IoT for Beginners, buy real hardware and work through the course, you can buy it directly from Seed Studio. So there's links on IoT for Beginners that takes you where you can literally just buy a kit with the hardware that you need. And you've got 3 hardware choices. One is microcontroller based, one is single board computer based, and one is virtual. So if you don't actually want to spend any money on hardware, got a whole virtual hardware set up where you can do the entire course without buying any physical hardware. We have a simulator that runs locally, and you can it's basically a web page where you add LEDs and set light sensors and speakers and all that kind of stuff to it, and GPS sensors. You add it to a web page and it runs as if it was the real hardware for a Raspberry Pi. So kind of great options. If you want to buy the hardware, you can buy it from Seed Studios as a kit. If you don't want to buy the hardware, we've got a full virtual option. So Walid says, hi all, I love IoT Fridays and all of you guys. Yes, we love you too. We all love IoT. We all love Fridays. And yes, I love you all. I want to share IoT with you. So welcome, welcome. Great to have you here. So IoT for Beginners is what we're working through. It's here. It's free. If you want to use it, just go ahead and use it. It's there for you. Jump on there. Give us a star. It's very popular. It's been used in classrooms around the world. It's been used for people to learn. So it's there for you. So let's dive right in. This rather probably hard to read diagram is a nice overview of everything we're doing today. So we're going to kind of do a deeper dive into the components of an IoT application and to microcontrollers and single board computers. So today is kind of all about the things. Next week, we look at kind of sensors and actuators. And the week after that, we kind of dive into connectivity and the internet side. So today is T. It's the T of IoT, all about the things. Let's jump in the chat, ask questions, let me know what you're working on, and let's just have a bit of fun learning IoT. So today we're doing a deep dive. We're going to look at the components of IoT applications. We're going to then dive deep into microcontrollers, talk about how they work, the hardware, the frameworks that they use, and then we're going to dive into single board computers, kind of look at more then the hardware and just kind of how they work. And so there's two components to an IoT application. Yeah, Internet of Things. The two components are the internet and the thing. I know it sounds a little bit silly, but that's literally, it's named after what it is. The interesting point about naming is a lot of people are starting to move away from IoT as a name. They're starting to focus more on edge computing. And then you have things like light edge or constrained edge for IoT devices. So if you start hearing people talk about edge computing and light edge or constrained edge, they are talking about IoT devices. So I've got an interesting naming fact for you there. But yeah, IoT apps are made of the internet and the thing. So the thing interacts with the physical world. I know we touched on this a little bit last week, but the thing has that physical interaction with the real world. They use sensors to sense the world around them, whereas light sensors, temperature sensors, noise sensors, and then they use actuators to interact back with the world around. Yeah. Turning on lights, making noise, opening garage doors, turning on switches. And they interact with the physical world, and then they connect to the internet or to other things via some form of connectivity. So kind of a typical example would be your thing has Wi-Fi, it connects over the internet, it sends data from sensors. On the internet side, you have applications that will gather this data, run reports, run analytics, make decisions, and then send requests back to the thing to do something. So kind of you usually have this, you may have just send sensor data, or you may have just send control messages to do something, or you may have a device that does both. And so the thing, this is where they're usually very small devices, small microcontrollers with kilobytes of RAM, running very, very slowly, hundreds of megahertz, not gigahertz, putting very low power potentially. We talked about this last time, running off maybe batteries or just very low power usage. And they interact with the world, and then they send data or interact with the internet. So the idea of these things is because they're running all continuously, they sit there and run all the time. This is where they have kind of low power requirements. You don't want an internet device that sends your electricity bill through the roof. You want to have a kind of a low power usage on that. So the canonical example is the thermostat. So back when I was a young kid, 40 odd years ago, the classic thermostat we had was a box on the wall. It had a little dial on it to set a temperature. And then they had a thermocouple inside. It's like a basic temperature sensor, thermometer essentially. And then when it detected the temperature dropped below what was set on the dial, it triggered a relay on the heating system to turn on the heating system. All very, very dumb. It wasn't a smart setup. It's just literally, as the temperature went below this value, the heating will come on. When it goes up, heating goes off. Okay. Now, the modern versions of this, the IoT versions, are completely different. This is kind of what I've got in my house at the moment. So I have got a smart thermostat on my wall, and that thermostat is connected to my HVAC, my heating and cooling system, but it's also connected to multiple temperature sensors around my house. And then what happens is it gathers all the data from the different temperature sensors, sends that data up to the cloud. So from my phone, I can see the temperature in my house. And then it uses that data to make smart decisions on what it wants to do around heating and cooling. It could be my downstairs is too cold, but my upstairs is warm enough. So don't need to put the heating on. Could be upstairs is too hot, downstairs is just right. Maybe put the aircon on because that cools the upstairs first. And so kind of you can use smarts to make smarter decisions. It could look at occupancy. My house is too cold, but there's nobody in the house. So why bother heating it? And then kind of get smarter and smarter from that. All the data gets sent to the cloud so they can run AI models to kind of train more efficient ways of heating. It's got eco modes on as well that looks at things like the temperature outside. It looks at the predicted temperature and uses that to make decisions. In the morning, if the house is cold, but the temperature is about to warm up during the day, maybe not put the heating on because the house then may get too hot when the sun comes up and all the sunlight comes to the front windows. And so it's not just this dumb on off. There's a lot of smarts that can be applied to it. You can get ones that connect your calendar so they know that you're not going to be around, so they turn the heating off when you're on vacation. You can get ones that connect to location tracking via your phone. So on your way home from work each day, it turns the heating on before you get home. Leaves it when you're out the house, leaves it off, turns on. So kind of a lot of cool things you can do with this. Now, Renee asked a really awesome question. How do you keep the data from your smart home devices being accessed by outsiders? Now, this is a great question. There's a joke that the S in IoT stands for security, because there is no S in IoT. So security is a really big issue around IoT devices. So you are trusting the provider of your IoT device, the one that has got the cloud service that manages it. You are trusting them to to manage your data. And you do have to hope that they don't make this data public. And there's a whole lot of horror stories. Literally, if you go and Google for IoT security breaches, you'll be shocked by some of the security breaches. Now, I'm an IoT nut. I have a few consumer IoT devices in my house, but there's certain things I will not have. I will never ever have internet connected cameras in my house. I've got one on my front door, never going to have one in my house. Too many horror stories. Never going to have. Luckily, my daughter didn't want any connected toys. Never going to have those because there's too many horror stories about people mining the data. Sometimes it's because they store it in a database in the cloud that's not secured, and people can just access that data. Sometimes the data just leaks. Sometimes they sell it. Renee does ask about like Facebook. If you connect your smart heating system log into Facebook, maybe they might be mining the data. They might be looking at your data and using that to serve up adverts. So there is a lot of potential for people to harness your data because this data gets sent to the cloud and you have to trust the cloud provider. Now, one thing that is coming is a thing called Matter, which allows you, it's kind of a consumer IoT standard that allows you to kind of control IoT devices without cloud services. And so the data gets aggregated and managed by a Matter hub. So you can use like an Amazon Echo or Apple TV to kind of control some of your devices. And that reduces the dependency on the cloud. That may make things a bit more secure. But yes, it is a known problem. It is a known problem. There's people who can access your data. Also, there's the ability to hack, so they can access your IoT devices and control them remotely. There's a great newsletter from Stacy on IoT. So if you just Google for Stacy on IoT, sign up for the newsletter, and actually this week's newsletter that came out this morning was talking about putting all your IoT devices on a separate Wi-Fi network than your phones and computers, just in case your IoT device gets hacked and they then connect to your device. So Irene asks, can you create an intranet? Yeah, it's kind of what Stacey is alluding to in her IT, Station on IoT newsletter, is you kind of have a separate guest network for things. And if you can even get hardware now that limits where your IoT device can talk to and kind of manage that data flow through. But the problem with a lot of consumer IoT devices, they want to get your data to the cloud so that they can run their processing there. So you kind of have to be very careful about choosing your devices to make sure that they don't harvest your data. So if you're really security conscious, maybe IoT devices are not the best thing to get because a lot of them have cloud services. This may change. There's been issues where companies have gone bust because they're selling you the device, they get your money once, and then they're running cloud services that cost them money. So then this may change with the rise of Matter, where you can control your devices. All your devices can be controlled from an internal hub. There may be less data going to the cloud. So things may change. It's a good area to keep an eye on. So Renee asks, name for the newsletter. Let me just see if I can get that. Here we go. I'll just drop it in the chat. I highly recommend. I'm not a newsletter fan. I rarely subscribe to any newsletters, but this one, I read this every week. I highly recommend Stacy on IoT. And then, their podcast talks about locking down smart home data. So it's a good podcast on that. And they talk about it a lot in this week's newsletter. So great question. Yeah, security and IoT is a fantastic topic to be aware of. Carnegie Johnson says, can we drill down on the sensor type that measures occupancy? So I'm going to be covering sensors next week. So today we're kind of drilling down more into the things side of things. Next week we're going to be going into sensors and actuators. Because there's a number of different types that can measure occupancy using some of them just use infrared just to kind of detect movement. Some use ultrasound. But yeah, next week we'll be diving into sensors. So remind me next week, and we can dig a bit more into that. Disco 12345 says, hi all. Hey Disco, welcome. Cool. Yeah, great questions. Yeah, security is a very big thing with IoT, absolutely huge thing with IoT. Yeah, it's always worth Googling for all the IoT security scares. Because there's definitely some devices that have been cloud connected and had some very interesting security problems. So yeah. Certain IoT devices I would never ever own. So we touched a little bit on a lot on the kind of the idea of a smart thermostat to make things happen. But some homework or something to kind of think about before next week. What other smart things you've got around your house? What other systems have you got that have got sensor data and use that to make decisions, whether they're dumb devices or smart devices? Just kind of have a think about the things you've got around you. What can be used, what could be converted to an IoT device to make more decisions? Carnegie's question about occupancy sensors. You get occupancy sensors now connected to IoT setups to manage heating in buildings. No one in a meeting room, turn the aircon off. Things like that. So have a think about this. It's a little bit of homework. Have a think about the systems around you that read sensor data and make decisions. So we talk about things. Let's move on to the internet side, the I side of an IoT device. So kind of the typical kind of setup is you'd have some kind of cloud service that acts as like an intermediary. And so all your IoT devices will connect to some form of IoT service. Yeah, so I work for Microsoft. We have one called IoT Hub, and that's basically a big pipe that you connect things to. But the idea is you'd have some kind of IoT service that all your IoT devices connect to. And these services handle things like security to make sure that only permitted devices can connect. And then what would happen is they would have all the IoT devices would send data to the IoT service, and then other services would take the data off the other side and do some kind of processing. And so usually your cloud service is literally just a big fat dumb pipe. Data comes in from devices on one side, comes off to applications on the other, comes in from applications on the other side, and then comes to devices. So your device sends temperature signal, what's the temperature value to the IoT service. That then gets sent to some kind of processing application. That decides you want to put your heating on, sends a message to the IoT service, comes off and goes to the device. And so the IoT application is what you build up on the internet side of things, where you build up your data processing, data storage, decisions, things like that. And if you joined me last week, you may remember I said that a data scientist is your best friend. As an IoT person, if you are building an IoT application, you are gathering data. A data scientist can help you decide what's the right data, how much data to gather, what you want to do with that data. So there's a lot of data with IoT. So data scientist is good for that. Now, Internet of Things devices don't always connect directly to the internet. Sometimes they have things like mesh networks or peer-to-peer networks where all your devices talk to each other and then potentially have a connected hub. So if you've ever done things, I think it's like Philips Hue lights, for example, you have like a hub and then you have lights that you put in, and the lights talk to the hub connects to the internet. And this allows these lights to connect using other protocols. So rather than putting a Wi-Fi chip on a light bulb, you can connect using something like Bluetooth or Zigbee or some other kind of connectivity protocol. So that way, when you add more lights, they all just connect to the same hub, and they're all managed by the same hub. So other times you get mesh networks where they rely on device talking to device, and only one will be close enough to Wi-Fi to get connectivity, and the devices just send data around to try and find the one that's connected to Wi-Fi. So there's kind of multiple ways that you can have devices connected. It's not always every single device is connected over Wi-Fi. Seen a huge rise in 5G as well for internet connectivity. Because the way 5G works, it's not just faster 4G. Because the way it works with kind of private 5G networks and network isolation and low power usage, you can get a lot of IoT devices that connect over 5G. So you can have like a factory that's got its own 5G network in there that connects via a gateway to the cloud, and then every single IoT device in the factory connects over 5G to the private 5G network. And they can use that kind of section of devices, almost like build up the intranet that Renee was alluding to. You can have like your own little separate, completely separate networks of 5G setups that send data via a hub and get managed. So kind of lots of different types of connectivity that devices can do. And so this is kind of the idea of this smarter thermostat. It's not just the on-off. So you start adding occupancy sensors and temperature sensors and calendar and weather data and make these intelligent decisions as you kind of bring everything together. And this is kind of the AI thing as well. It's not just a data scientist that can be your best friend. An AI machine learning engineer can be your best friend, because sometimes when you make decisions, you might need some AI models to help with predictions. So there's kind of a lot you can do with AI, folks. Ducasoft says, was sure Philips LEDs could relay signals from other LEDs to the hub. So you mean, yeah, so as in each Philips Hue bulb, yeah, they kind of work on what's called a Zigbee, kind of a mesh network. So each bulb can send to other bulbs, and they all kind of help route data to the hub. It's kind of like you get like a whole mesh network. So Zigbee is the protocol. It's kind of that's designed to be a mesh. So it kind of uses other devices to send data around. So you don't have to. So you don't need to have every single bulb be within the right distance to the hub. As long as each bulb is close to another bulb, it can go from bulb to bulb to bulb to bulb to hub, which is pretty cool. This kind of mesh networks are great. I did a cool project a couple of years ago using BBC microbits. So you can actually gather sensor data to BBC microbits, and then they would send those via Raspberry Pi to the cloud. And as long as each microbit could see one other microbit, you could actually hop that from microbit to microbit to microbit to microbit to microbit, then to the Raspberry Pi to the cloud. So mesh networking is brilliant. Your connectivity has a limited range. So if you've got, I don't know, sensors in a farm, for example, you could actually have, as long as each sensor is close enough to send a signal to another sensor, you can build up a mesh network across a really huge area and just have one Wi-Fi connection at one point in the mesh. So mesh networking is cool. Very hard to build. When I built one for BBC microbits, that was a challenge. But mesh networking is very, very cool. So another bit of homework for you to think about. What other data can make your thermostat even smarter? Kind of mentioned that, yes, it's temperature data, weather data, calendar data, occupancy data. What else could make a thermostat even smarter? This is kind of where we scale up to commercial IoT. So imagine you've got a massive skyscraper, 120-story skyscraper, and you want to keep the energy usage down. What data could you actually use to make the thermostat even smarter to make decisions? Occupancy, yes. Weather, yes. What else? Have a think about this. Some examples could be lift data. So as people are coming up and down the lifts, how much the lifts are moving. So what's happening to people? Things like that. So have a think about it, and we can maybe talk about some of this next week. Now, IoT devices don't have to connect to the internet. You can still be an IoT device as long as you're connected to something that helps you be smart. And the classic example of this is edge computing. Now, edge computing is it's a very much catch-all term. I mentioned earlier, we're talking about kind of light edge, constrained edge for IoT devices. But edge computing is about taking the processing from the cloud to what we call the edge of the cloud. And so it's kind of managed by the cloud, but run on the edge, kind of on your local network. So I'm going to just jump on this comment quickly. Shotoko Tech says varying electrical rates throughout the day. Yes, that is a really, really good one. Just going back to the question about the make a smart thermostat even smarter. Yes, electrical rates can change throughout the day. During the day, there's a huge demand for electricity as like factories are running. At night, the demand drops, prices go down. So in the UK, for example, where I used to live, you actually could be on a system where you pay more for electricity during the day, but a lot less at night, and then you'd heat up storage heaters. So the heating system would be you'd heat up a massive block of concrete at night, and then that gives out heat during the day, which is very, very cool. So you could kind of do that with buildings. You could have that kind of storage heater type system where in winter, during the day, at night, you heat up a big block of concrete in the middle of the building, and then the heat gets let out throughout the day. Or if you know there's going to be a hot day, you run the air conditioning really strong at night to cool the building down a lot, so it's cold when people come in, but then it doesn't get too hot during the day. So yes, very electrical rates. Great idea for that. And Carnegie Johnson says humidity and air quality. Again, yes. I mean, my thermostat here actually monitors humidity because that affects how you feel the heat. If you've ever been to Southeast Asia, for example, the humidity there, the 100% humidity, you really feel the heat. Whereas when you go to kind of a more dry desert type place, it's the same temperature, but you don't feel the heat as much because the air's so dry, so it doesn't kind of transmit to your skin. So humidity is very important. Air quality as well. Yeah, great stuff. Great stuff. So yes, IoT on the edge. So the idea of the edge is it's not kind of going back to kind of on-premise networks that the thing we had before the cloud. The idea is it's an extension of the cloud. It's managed and controlled by the cloud. So what you can have is you could have an edge device that's got all your decision making. So when it comes to your HVAC decision making around monitoring all the different data and making decisions, what you can do is you could train an AI model in the cloud, take advantage of the kind of scalability of the cloud, train your AI model, and then deploy that to a device that runs locally. And then all your IoT devices, they connect to your edge device, and the edge device makes the decision. And that edge device could then send data up to the cloud to retrain the models, to gather data for the future, kind of whatever. But all your IoT devices connect to the edge device that makes the decision. Going back to Renee's point about an intranet for this is kind of like that. An edge device is kind of like that. Obviously, it's something you have to custom build. You won't get that with consumer IoT devices, but a lot of things we use this. It's much faster than the cloud because the network hop is much shorter. So they use this a lot in factories when you're monitoring vibration of machinery to work out for predictive maintenance. If it's doing this, it's fine. If it does this, it's about to break. You've got to make a decision quickly. You don't want to send the data to the cloud and then not be able to respond in time. So you can actually do it on the edge device to make a decision quicker. The classic example I say is you don't want to find somebody is using up your bandwidth watching Netflix in the break room and you don't have time to make a decision on data. In fact, Kamal actually says this, IoT on the edge is important when you need little latency to react or make decisions. Yes, because that very short network hop, that's usually the biggest time constraint. Running AI models can take a lot of power, and it's unlikely your edge device can run your AI model at the speed the cloud could run it, but the difference is negligible compared to the network hop. I make a local network call over my 10 gigabit network backbone. I get it doesn't matter whether the model takes a millisecond to run in the cloud or 2 milliseconds to run locally. If it takes 10 milliseconds to hit the cloud and 1 millisecond to hit locally, it's still going to be quicker. So edge devices help make it faster to respond. Maybe not so important for an HVAC system for heating and cooling, but if you want to stop a machine from breaking, if you've got some big machine that's thumping away and you've got to make sure there's no one around, as soon as it detects a person nearby, it shuts the machine off. You've got to be quick. So it's great for that. Napalm664 says, hi, by the way. Hey, great to have you back. Thank you for joining us again. You have to be careful about battery life, though. We're actually doing this in a project now. Yes. So any IoT devices that run off batteries, you do have to be careful about battery life. So it doesn't matter how fast you can process the data. If your battery is flat, then you can't respond to that data. So you do have to think about power. Power is a huge consideration for these devices. If they run off a battery, then you kind of want to have some kind of setup where you're regularly changing batteries. I was reading some great articles around Bluetooth beacons back when they were a big thing from Brooklyn. There's a Brooklyn art gallery, not art gallery, a museum, the gallery in I'm losing words. I can't do words today. There's So there's a big museum in Brooklyn where they had they used Bluetooth beacons. They put them by the painting, so when you go near a painting, your phone picks it up and tells you all about what that painting is. But they actually had to have planned time to go and change the devices over and change the batteries because the batteries kept running out. So they actually had to plan this. It was literally scheduled maintenance of every 6 months. We go and change all the batteries and all the beacons, whether they needed or not. I've got a battery-powered electric front door. So my door, I type in a code and my door unlocks. I change that battery once a year, whether it needs it or not, because I've got so used to it, I don't take keys, and I don't want the battery to run out and I can't get into my house. So Napalm 684 says, yeah, I work in medical devices. They typically promise a day of use. Yes, so medical devices especially, the battery thing is important. Yeah, you don't want to find that you're relying on a medical device that's gone flat. So you want to make sure you manage that battery usage. I mean, I'm a type 1 diabetic. I've got the sensor on my arm, and this has got a 2-week lifespan in it. So it's triggered by NFC, and it runs for... the battery probably lasts for more than 2 weeks, but it's got a hard cutoff at 2 weeks so that I don't have to worry about it running out of power. So battery is hugely important. Rene asks, Brooklyn Museum, Brooklyn Academy of Music. Trying to remember which one it was now. Trying to find the... So if I can find the link to it. There was... yeah, here we go. So yes, it was Brooklyn Museum. I've just dropped the link, and I think it's quite interesting. Should have stuff on there, but yeah, they use these beacons, and they have a limited battery life, so they're kind of just managing the idea of... Yeah, here we go. In the end, beacons are standalone battery-operated units. Great because they don't need power. Unfortunately, unlike a hardwire system, there's no reliable central management tool for beacons. So, beyond actually going to galleries and taking a look to see if units are still there and or working with the scanner app, we have no way to know what's happening on the floor. So they're kind of managing the battery use. Yeah. So they had to change batteries and potentially check. Well, these ones have fixed batteries in them, so they had to kind of change the devices. They had to literally replace the devices. But it's kind of a really interesting article about how they did a Bluetooth beacon deployment from a few years ago. So yeah, batteries, power, very important thing to think about. So IoT security. Yes, touching on this again. I know, Rene, you were asking about this. Yeah, the S in IoT stands for security, but there's a lot of problem with IoT security. And yeah, this can have real world consequences. Recently, there was talk of one of the big pipelines in the US got taken out. Security is very important. You don't want to take out an actual pipeline that provides fuel for millions of people. There's a famous one, the Stuxnet worm, which was in Iran, where they had centrifuges for working with nuclear fuel. Not going to go into the legalities of all that, but essentially there was a virus released that got into these centrifuges, and they changed the signal from the speed sensors. So it thought it was slowing down, but so it tried to speed it up, and it went faster and faster and faster, and actually broke the hardware. So they caused a hardware fail by using a virus. Allegedly, it was done by the US and Israel doing a cyber attack on Iran. No idea what the actual story is, but yes. Yeah, these can be used in cyber attacks to damage hardware. Security is very, very important. There's rollouts of smart monitors. So there's a lot of places around the world where they're starting to put smart electricity meters around everyone's house. So that means that you can be charged the right amount of electricity. They can get better data to monitor electricity. If somebody hacks that network, imagine turning off the power to 50 million people. So consumer IoT has a lot of hack potential. And just accessing people's data. There have been baby monitors that have been open. So people have been able to connect to someone's baby monitor and literally peer into the child, even talk to the child. There's been cases where somebody's been talking to a baby in a car, and it's pretty horrific. And it just goes on from there, on from there, on from there. Say, just Google this, fire up Bing, Google this with Bing, and just search for some of these hacks. There are some hacks of a very not safe for work nature as well, which should be considered. And some of these hacks are not done as direct hacks. Some of this is done via social engineering. So AT&T were putting smart cameras in people's houses, and one of the installers managed to convince people he found attractive to give him access for maintenance purposes, so he was able to spy into people's houses. And this is pretty scary. So yes, always approach devices with an open mind. That's what I said. I will never have a cloud connected camera in my house. Not going to happen. Never. And there's a few other types of devices I'm never ever going to have in my house. Napalm684 says, Google this with Bing. So search for Bing on Google, then look for IoT security and hacks. Genius. Yes. No, we all use Google it as the term for searching. But obviously I have to stay on brand. So, you have to just Bing it. Yeah, doesn't sound as good, does it? So one interesting way to do security is air gapping. So the idea of air gapping is you literally are not connected to the cloud. This is kind of where edge computing can be great. You can actually set up Napalm664 is just giving me grief. That's fine. It's all good. All good, my friend. All good. So yes, air gapping is a way to be secure by just not having a cloud connection. So you could actually train your AI model in the cloud, and then you could stick it on a USB stick and install that on a private internet to keep it secure. So that's one way to do it. If you're running any kind of critical infrastructure, you may want to think about having things air gapped, just for that level of security. You can't hack it if you can't connect to it. You still obviously can hack it. You can go as long as if you can get physical access, but it just adds that kind of extra bit of security space. Fuel Snable says, easier to say than just MSN search it. Oh, that's retro. That's retro. Fire up Lycos and do a search on Lycos, going back some. Cool. So another bit of homework for you. Think about security challenges or security scenarios for the IoT systems around you. And fire up MSN search and have a look around, find some of these security issues. All the web. Oh, that's going back some. All the web. But have a search. See if you can find some hotbot. Got it. For old people like me, hotbot, all the web, Lycos search, Yahoo search, when these were a thing. That's going back some. But yeah, so have a think about security, do some research, get onto your favorite search engine and just search for some IoT security scenarios. And then don't blame me if it makes you want to throw away some of your consumer IoT devices. Right, so let's dig into the things. Let's dig a little bit into some of the hardware side of things. Let's talk about microcontrollers. So microcontrollers, these are a combination of like a microprocessor, a teeny tiny little CPU essentially, with things like a bit of memory, a few other bits and pieces, just kind of usually kind of one board or chip that's got just enough to run some code. And these can be connected to these you connect to the cloud to send all your IT data. You've got kind of a CPU in there that kind of does all the processing. And now whenever CPUs work, sorry, there's a retro comment there from Carnegie Johnson. Ask Jeeves. God, that's also going back some. Wow. All you young whippersnappers probably don't know what we're talking about, but these are classic search engines from 25 years ago. Maybe a longer, more than that. I feel old. Yeah, so CPUs, they tick. So you have a clock that ticks, and each tick is kind of when it does some form of execution of an instruction. Okay, so usually what you have is a thing called the fetch, decode, execute. It's kind of digging a little bit into how kind of CPUs work. And so every tick, it'll get some data from RAM to tell it what to do, the next instruction, decode that instruction to kind of what that is, and then execute that. And that will then do something. And then this can be like one tick or it can be multiple ticks. So every time the CPU ticks, it does some of these things. It will grab the next instruction, process it, and then do that next instruction. So that's kind of what we talk about, what a clock tick is. And then depending on the instruction, copy a value into a register. So basically take it from RAM into some of the CPU can do. That's kind of one tick. Add two numbers, one tick. Divide some numbers, more ticks. And so each instruction takes one or more ticks. And then every tick generates heat, uses power and generates heat. And so when you think about the microcontrollers, when we talk about things like the clock speeds, when we talk about the clock running like 1 megahertz or 128 megahertz or 8 megahertz or 4 gigahertz in the case of your computer, that's that gigahertz is or megahertz is the amount of clocks. So a 4 gigahertz computer would have 4 billion ticks every second. So every second it can run sort of 4 billion of these cycles per core, and there's kind of more cores, and it can actually run some of these things in parallel. But each one of these draws power and generates heat. And so this is why microcontrollers run slower, because each of these cycles, so you use power, a microcontroller runs slower, and that cuts down the power usage. So if you've got an 8 megahertz processor, that's 8 million ticks a second, that uses substantially less power than one that does 4 billion ticks per second. And where it uses less power, it generates less heat, so you don't just cool it down. If you've got a computer with a fan, it's because every time it ticks, it's generating heat, and then you need the fan to cool it down, which takes up a lot of power. So microcontrollers run slower, don't have cooling, keeps the power down. That's kind of really, really important for microcontrollers about how it keeps it down. Now, microcontrollers have 2 different types of memory in them, same as your kind of computer, your desktop computer does, or your laptop has. You have your program memory, and this has got the actual application code running on the program memory. And this is there. You turn it off, turn it back on again. Program memory is there. On your computer, you have a hard disk, SSD, or spinning Rust, whatever it is, whatever hard disk you've got. The program memory of the microcontroller is basically that. So your flash storage, it's your memory where your program lives. And that's when you boot it up, the bootloader, the thing on the microcontroller that makes it work, goes to your program memory and gets instructions for work. Then you have your random access memory, your RAM, and that's what's used to run your application. That's where your variables are created and all that. And that is what gets reset when you turn the power off. So that kind of controls the state of your computer. Same as on my laptop here has got half a terabyte of storage. So that's the program memory, and that's got all my photos and applications on there, and it's got 8 gigs of RAM, which is what's used to run the application. Microcontrollers have that, just a lot smaller. Phil Snable says, my Atari ST was an 8 megahertz computer. Yes, a lot of computers back in the day were 8 megahertz. So that's kind of one of the first, a lot of chips kind of used to run at that. I had a ZX Spectrum, 8 megahertz. But you couldn't really get 8 MIPS out of it. So MIP is millions of instructions per second. With computers like the 8 megahertz computers, you don't always get 8 million instructions, because some instructions take more than 1 clock cycle. You want to add 2 numbers, you've got 1 clock cycle to get the number from memory for the first number, another clock cycle to get the second number, another clock cycle to add them, and then another clock cycle to get the number out. So you kind of get, and some instructions like divide instructions can take more. So you don't always, it doesn't mean you get 8 million things happening per second. It's just it tries to do 8 million things, and some things take more things. So microcontrollers, this is where the memory is a lot smaller than what we're used to on our PCs and laptops. So as I said, I've got a MacBook Pro, 8 gigs of RAM in this thing. It's more than enough for an M1 processor. I've got a Surface Book with 16 gigs of RAM in it, and I've got a Weird terminal, which is this little device here. Little microcontroller. It's in a big box because it's got a nice screen on it, and that has 192 kilobytes of RAM. Not even megabytes. So it's not even, we're talking, if I had 8 of these, it will be a megabyte. No, not 8, 6. I can't do maths. It's too early in the morning. About 6 of these for a megabyte, and so I then need 6 for a megabyte, and then 48 for 8 megabytes. So 48,000 Weird terminals to have the same amount of memory that runs on my PC. And so it's because it's substantially smaller. Each byte is enough to store one number from 0 to 255. Because it's substantially smaller, I have to think about new coding paradigms for what I build. I have to think about keeping memory down. Lots of questions coming through. This is interesting. I actually want to control my room lights and fan by my mobile. Is it possible to control 2 rooms in my house using 1 microcontroller? Yes, you can. So although those microcontrollers are not that powerful, you can have multiple connections coming out of them. So if you want to send a signal to a relay, yes, you can. I mean, you're saying using a basic Raspberry Pi 3B. They're pretty powerful devices, Raspberry Pis. So these aren't even microcontrollers. These are Linux computers. But yes, you can control multiple things. It all depends on kind of what setup you've got. But yes, because when you turn a light on, it's usually just a simple signal to say on. Yeah, I've got lights here. When I change the color of these lights, I'm not sure how well you're going to see it. If I tap a button here, my Raspberry Pi Zero changes the color of the lights. It's kind of purple and all these different colors. My Raspberry Pi Zero just sends a signal to the lights and say change color, and they change, and that's it. So yes, one Raspberry Pi is enough to power a whole load of things. So yeah, if you want to actually physically connect those devices up to it, yes, absolutely can power those. Or if you've got a load of consumer IoT devices, there's a thing called Home Assistant, runs on Raspberry Pi that can manage a whole devices for you. But yeah, totally powerful. Fuel Snable says, I read that on the old Apollo computer, if it did multiple divide instructions, you could overheat it. Yes, I can imagine that, because when you're doing a lot of divides are usually quite computationally expensive. So you're doing a lot of divides, that's going to warm up the processor. So yes, you could overheat it. Napalm684 says, not running C# on that guy. That's where you are wrong, sir. You are wrong. You can run C# on a microcontroller, but you can't just do using the standard desktop C#. So there's a thing called Nano Framework. And Nano Framework, it's mentioned in gelati.dev. I'll just drop a link in the chat. Nano Framework actually compiles down to take C# code and compiles it for embedded systems. So you can run Nano Framework on various MCU devices. I don't think they support the Weir terminal, but you want to got like an ESP32, kind of the classic beginner Arduino type device, you can run .NET Nano Framework on that. So yes, you can run C# on that guy, but it's just not the desktop one. This has to be one that gets compiled down to embedded code. Fuel Snable says, throw in a few no-ops. Yeah, so no-op is no operation. So if you want to reduce the heat, you basically put some kind of delay where it says do nothing to let the temperature come down. So no-op can do that. Carnegie Johnson asked, is big engine versus little endian still a thing in the IoT ecosystem? So this is all about how you store numbers that are bigger than 255. And you either, so these numbers become 16 bits rather than 8 bits, so they take up 2 bytes. And then one is kind of the bottom end of the number, one's the top end of the number. And it always varies. They're either stored bottom then top or top then bottom. That's the difference between little endian and big endian. It kind of is if you want to optimize your memory. So when you think about when you're trying to put things in a small amount of memory, if you're taking a block of memory and then saving that into flash storage and then reloading that, you have to know how to decode that memory. So yes, you do have to consider how much, how the number is stored if you're just saving raw binary buffers of data down to a device. But yeah, it's like going back to kind of classic C++ code, because you program microcontrollers C++, and then you have to work out how you store data, how you store numbers. So yep, it's still sometimes a thing around data storage. You've got like an object, you want to write the object as binary data to disk, and then decode that back. It's still a thing. Napalm64 says less than a megabyte of RAM. Maybe I missed something there. If this is for .NET Nano Framework, yes, it compiles down small applications, so you can run it on any small device. Because it compiles down to embedded code, so it's not running .NET. It's taking .NET and compiling that down. So you're kind of getting raw embedded code that comes out the other end. So yes, it will run quite happily. I mean, here you go. This is an ESP Room 32. Runs quite happily on one of these because it is literally very small compiled code. It's not running garbage collection. It uses a whole kind of tracking system for managing memory. But yes, it's insane, but it works. Yes, as Napalm684, as you say, that's crazy, but it works. It's fantastic. Protec 0508 says, I'll try this weekend. Thanks. We'll see the parts I need, like ESP8266 Wi-Fi modules, relay for different connections. Yeah, there's a lot of great stuff you can buy. So the lights I've got here, they are programmable LEDs, and they are just used by these WS8212 programmable LEDs, and there's libraries to control them. So you can actually buy a lot of these kind of kits that have got the stuff done for you already. So rather than you having to get down to electronics yourself, you kind of buy a lot of cool kits for it. But yeah, things like fans. I mean, one thing I do is I use smart plugs. So when I press a button on my desk to turn my lights behind me on and off, the lights on my Lego are managed by a smart plug. And so I use IFTTT. So I press a button here, microcontroller that this is connected to sends a signal to IFTTT, and that actually turns the smart plug on and off. So you kind of add things like smart plugs to do power. So you want to control a fan, you can maybe use buy a fan that's already internet connected, and then just on your IoT device, use that to make a call over the net to control it, which is pretty cool. Shotaku Tech says, just the .NET bits needed, not the whole package. Yes, so when you compile .NET Nano framework, it has a linker in there, strips up the code you don't need. So you just get the bits you need compiled down to go on the device. It's super cool. Every Friday throughout July, we've got another article coming out on julyit.dev all about it. So there's 2 there now. One came out last week, one came out today. Today's one's about GPIO, I2C, SPI, and IO support. Articles coming out every Friday at julyit.dev. So check it out. So yeah, so microcontrollers, very, very small memory footprint. So you've got to think about how much you store. Now, microcontrollers have GPIO pins for managing data coming in and out. So if I get my camera here, flip this one over, got pins here. The idea is you have this kind of connectivity. You would connect hardware over the GPIO pins. This allows us to get data in and out and kind of control sensors and actuators. And most of these are GPIO, general purpose input-output pins. And so they're kind of programmable. You can say whether you want to send voltage, receive voltage, and that allows you to kind of interact with devices. Now, microcontrollers, very, very small. You think about, this WIO terminal here, for example, 72 millimeters by 57 millimeters by 12 millimeters. This is smaller than the CPU in an average PC. Just the CPU for PC is bigger than my WIO terminal. And you can actually get really tiny microcontrollers. The smallest one is the Freescale Kinetis, which can fit in the dimple of a golf ball. So this is tiny, absolutely tiny. Fuel Snable says, I thought GPIO stood for Google Protobuf IO. I'm not sure that's trolling or not. No, it's general purpose input output. So, and Pratik says, I wrote ASP.NET web development requirement. Yeah, if you want to run, so Raspberry Pi would be great. You can actually put ASP.NET on, because you run .NET Core, ASP.NET Core on a Raspberry Pi, set up a whole web service, and then use that to manage everything, which is very cool. Yeah, Fuel Snable likes to throw some trolls. Can't help themselves. That's fine. We're all friends here. It's all a bit of fun. All a bit of fun. So yeah, microcontrollers can be very, very small, which is great for putting in constrained devices. You can buy rings that measure your activity and sleep pattern. So think how small the microcontroller has to be to go into a ring to gather data. Very, very small. Now, the way microcontrollers run, we're almost out of time here. So you may all have to head on to RT for Beginners and kind of read the rest of this. But the way microcontrollers work is they have some kind of framework to make it work. Microcontrollers don't run an operating system the way that your Mac, your PC, or your Linux device has an operating system. You don't run multiple applications. Right now I've got PowerPoint, I've got Edge, I've got Camo Studio, I've got VS Code, all running on my Mac OS. Don't get that with microcontrollers. They usually have some kind of very small framework that makes it work. And this framework knows how to run your code, because an operating system uses a huge amount of power to get a framework like Arduino that runs your code. Now, the operating systems you do get for microcontrollers are called real-time operating systems, or RTOS. And they are usually just get them as source code. And they are very constrained operating systems that just essentially give you a framework for doing things that an operating system allows you to do. Things like multi-threaded code, responding to real-time messages, networking, maybe even GUI components for microcontrollers with screens. So they kind of give you some of the features you would get from a an OS. Think the features get an OS of like 40 years ago, because they're that constrained. But that's kind of what an RTOS will give you. So it's not really an operating system as such. It just allows you to do things like multi-threaded code, makes networking easier, or handles interrupts for real-time messaging. So there's one called like Azure RTOS, for example, which is designed to connect to Azure. And you kind of, when you build with Azure RTOS, you just put in the bits you need. So if you want to do multi-threading, you just put in ThreadX. You want to do GUI work, you put in GUIX. You want to connect to the internet, you put in NetX. So you just compile in the pieces you need, and this gets compiled into your application. So that way, with the linker that strips out the bits you don't need. So it kind of gets compiled in. So it's kind of important to think about. You don't run an OS, you compile the OS into your application. So you just get the bits you need. So there's a load of different types of RTOSs. There's Azure RTOS, Free RTOS, Zephyr RTOS, a whole lot of different types of RTOSs. Now, a popular framework, if you don't use an RTOS, is Arduino. It's an open source electronics platform for software and hardware that allows you to kind of write applications in C++ designed for IoT devices. And the Arduino framework is based around essentially two functions in your code. Setup gets run once, loop gets run every time. So when the bootloader that's part of Arduino runs your setup code first, then just runs your loop again and again and again. That's kind of the OS that you've got as such, is you've got run this code first, run this code in a loop forever. So that's kind of one thing you want to kind of dig into is Arduino. Now, I'm going to have to cut things off there because we are at time. We have other streams happening, so I do have to cut off here. But thank you very much for joining. If you want to catch the rest of this, so this is all an IoT for beginners. We are working through lesson 2. So if you go to aka.ms/IoT-beginners, we're working through lesson 2, a deeper dive into IoT. It's all here. If you want to read the rest of it, but catch up before next week and learn a bit more about Raspberry Pis, go for it. It's some great discussion here today, which obviously is great for everyone. We all get to learn something. So thank you very much for joining us today. It's brilliant. It's been a really good day. Join us next week where we actually do lesson 3 and we look into sensors and actuators. And we'll be talking a bit more about how your device interacts with the physical world. But yeah, thank you very much, and see you next week.
Thank you, everyone, and thank you, Jim, for joining us today. If you have any feedback, we'd love to hear what you have to say. Please fill out the survey. I've added it in the chat as well as on the screen. Like Jim said, he will be back next Friday. I have added the screen to the chat as well as added it down below. Thank you, everyone. Until next time. Bye.
Thanks. Bye.